All right. Hello and welcome. Today we are going to be looking at organic compounds. That's what we are going to be touching on today. We want to look at the different organic compounds we have and their reactions and so on and so forth. So let's start off with the learning objective for this particular topic, and we are going to be focusing, and it's expected that by the end of this lesson, you should be able to do the following one: classify and name different organic compounds, draw and interpret structural and molecular formula, identify functional groups and isomerism, describe the properties and chemical reactions of hydrocarbons and functional groups, understand polymerization processes and the applications of organic compounds in real life. So these are some of the things that we're going to be touching on in the course of looking at organic compounds. So you're welcome once again, and I remain your teacher, Anjorin Oluwafemi Excel, and I'll be taking you through this organic compound topic, and we look at the different objectives that we have that you need to be able to have an understanding of. So without much ado, we'll move on into the content proper. Okay. Introduction to organic chemistry. Organic chemistry is the branch of chemistry that deals with compounds of carbon. It deals with compounds of carbon, except for oxides of carbon, carbonate, and simple salts. So organic chemistry is basically the branch of chemistry that deals with compounds of carbon, and with an exception of oxides of carbon, like CO2, like CO, carbonate, different carbonates, and then the simple salt. So those are the exceptions. So it deals with compounds of carbon. That's organic chemistry. Organic compounds form the basis of life and are central to the structure of living organism. Yes. When you look at the human physiology, or you look at the human body, or even life in general, you discover that most of the items that we have are from organic compounds, you understand. Organic compounds form the basis of life and are central to the structure of living things, or living organisms. So we must take note of that. We also need to talk about the uniqueness of carbon, because the reason why we can set out a branch of chemistry to study carbon and its compounds, or carbons that are compounds that are formed from carbon, is because of there's a particular uniqueness of carbon that sets it apart from every other atom. Now, one of the uniqueness of carbon is that it forms four covalent compounds. It is tetravalent. That's the word in chemistry. So it forms four covalent compound, and that makes it very unique and very important, also germane and very fundamental to organic chemistry. It forms chains, branches, and rings. That's another uniqueness of carbon. It can form chains, so it will bond together with each other, and it forms chains. It can also branch out, from the main chain. You can have branches that are set off from the main chain and all that like that. It can also form rings, where we have the cyclic, organic compounds like the pyridines, the aromatic compounds, and so on and so forth like that. So it also forms rings too, okay? Benzene and so on and so forth, okay? Another uniqueness of carbon is it can form single, double, or triple bonds with each other. So you can have a carbon-carbon single bond, a carbon-carbon double bond, a carbon-carbon triple bond, as the case may be. It's quite unique, and it's very peculiar to carbon. So that's that. Example of organic materials, like take for instance, you have fuels, you have plastic, pharmaceuticals, and DNA. These are examples of organic materials that are formed from from organic compounds you get. So we have fuels. Fuel is an amalgamation of so many carbon compounds coming together, and then giving us different types of fuels. Not only petrol, we can also have kerosene, diesel, and so on and so forth like that. And these are organic materials that are formed from chemistry of the organic from organic compounds. Then we have pharmaceuticals, which is an offshoot from from organic chemistry, because it is from there we can develop pharmaceuticals, then the DNA and so on and so forth like that. So these are all examples of organic materials. So like we can see, you can see carbon bonding in that way, forming different materials, From the knowledge of organic chemistry, you can form different materials. You can derive so many things, from the knowledge of organic chemistry, you can, manipulate carbon atoms and make them to be to be positioned in a certain way to form certain compounds of certain materials that can be very useful to humans and to that kind of hold very good economic usefulness, so to speak. So what are the classes of organic compounds now? Organic compounds are classified into several groups based on the functional group that they contain. So we can have hydrocarbons, which contains only carbon and hydrogen atoms. So you can have hydrocarbons containing carbon and hydrogen atoms only. You can have under hydrocarbons alkanes, which is a single bond, hydrocarbon. So you can have alkanes, you can have alkanes, one or more double bonds, alkanes. You can also have alkynes, one or more triple bond, existing. So these all fall under hydrocarbons. So then we have other classes of organic compound as oxygen-containing compounds. They are oxygen-containing compounds. Let's look at some of them. Alcohol, where we have the OH functional group. Alcohol is an oxygen-containing compound. That is a class of organic compounds. Then we can have aldehydes, which has a CHO, functional group. And then you can have the ketones, which has the C double bond O functional group, and then we can have the carboxylic acid, which has a COOH, functional group. So the carboxylic acid. Then we can have the esters, the COO functional group. And the next one is the nitrogen-containing compound, is another class of organic compounds, which we call the nitrogen-containing compounds. So what are they? We have examples like amines, that has the NH2 functional group. Then we have you know, it means basically that contains the NH2 functional group. So functional group determines the chemical behavior of compounds. So if you want to look at, if you have alcohol reacting in a particular reacting with another chemical or another compound, one of the things that will determine the behavior of alcohol is its functional group. It's a unique characteristics of all organic compounds, their functional group. So you have alkanes with a single bond, which is like the functional group. It compels it to a particular behavior and compels it to a particular reactivity or reaction, so to speak. So functional groups determine the chemical behavior and of compounds. So certain functional group will either limit an organic compound from being able to react, or actually give it the propensity to be able to, get involved in so many reactions, and so on and so forth, and the kind of bonds and kind of linkages or interaction it will have with all the compounds are all determined by the functional group, which compels a particular behavior or characteristics on that particular compound. Okay. All right. So looking at the hydrocarbons, which are alkanes, alkenes, and alkyne. So alkanes basically are saturated hydrocarbon with single bonds. They are saturated hydrocarbon with single bonds. Example includes methane, CH4, and ethane. Why do we say they are saturated? They are, their bonding space is fully occupied, by an atom. Like for methane now, you have carbon central, they have 4 atoms of hydrogen, bonded to it like that. So you discover that it is saturated, cannot take on any other. And ethane, the same thing too. So if you want to bring any other substituent or compound or atom to it, that means you need to knock something off from the main what's it called, or the original compound, in order to be able to accommodate whatever atom that you want to introduce to it. Okay, so we have alkenes. They are unsaturated hydrocarbon with at least one double bond. So don't forget, alkanes have single bond alkanes have double bonds. So you have the example as it's 18, C to H4, 18. And if you notice something, you discover that two hydrogen atom is has been taken away from ethane to give us 18, C2H4. So in place of the two hydrogen atom that was taken away, you now see the double bond being introduced, so to speak. So it has one double bond, in a structure. So the next one is alkynes, and this is also an unsaturated hydrocarbon with at least one triple bond. An example is ethyne, C2H2. That's C, the triple bond C, then HH on the terminal ends of both carbons. So that's for ethyne, or and is an alkyne, which is an unsaturated hydrocarbon. Okay. So this is the structure. So we have the alkane, which is an example ethane, which has a single bond, and it is saturated, just like I said. It is fully occupied by atoms. The atoms revolved around the hydrogen atom rather revolves around the two carbon atoms. So it's a saturated hydrocarbon, and it's single bond. Then alkanes, on the other hand, is it has just one double bond. It is unsaturated. Alkynes has it's triple bonded. That's triple bonds. That is C to C triple bond is what exists in that. So these are the hydrocarbons and their different classification. Okay. So hydrocarbons are major for us, natural gas, petrol, and diesel. So yes, yes, exactly. We can also read up, on our own, looking at hydrocarbons and the constituents. What are the things that we can derive from hydrocarbon? We can get fuel, we can get LPGs, we can get diesels, and so on and so forth like that. So we can also read up on our parts and try to look at them. Okay. All right. Now let's move along now. Talk about high-impact naming of organic compound. High-impact naming simply means that what is the fundamental way in which has been spelled out by International Union of Pure and Applied Chemistry to name organic compounds. So what are the rules for high-impact naming? Number one, identify the longest carbon chain. Identify the longest carbon chain. This is a very, very basic and fundamental rule in naming any organic compound. You must first identify the longest carbon chain, and that will also inform the root name of that particular compound that you're dealing with. Okay. Secondly, we number the chain from the end that is nearest to the functional group. So you number the name from the end that is nearest to the functional group. So the functional group, the end that contains the functional group, either the OH functional group, the double bond functional group, the triple bond functional group, or whatever functional group that we have, that is the end that you will start naming from, or put your carbon one at. So that's that. Then indicate the position and name of substituents. This is very important. So if you have substituent like maybe chlorine, fluorine, or a methyl group, you must be able to indicate their position. Is it on position one, or is it on carbon one? Is it on carbon 2, carbon 3, as so on and so forth? So you must be able to indicate the position and name of the substituent. And then we apply prefixes and suffixes appropriately. So applying prefixes and suffixes appropriately is very important. So these are some of the things that are very, very germane. Prefixes are what comes before, the compound. Suffixes are what comes after. So we must be able to apply them appropriately. Let's look at an example. We have CH4 as methane, okay? Then we have CH3, CH2OH, ethanol, okay? Then we have CH3, COOH as ethanol. How did we arrive at this? For the ethanol, you have two carbon atoms. Then you have a functional group, which is OH. So that tells us that it's an alcohol and it has two carbons. And two carbon is like ethane and the likes like that. So that's why we have ethanol. The same thing with the ethanoic acid. You have two carbon atoms. Then it has the functional group COOH, which is the carboxylic acid functional group. So that gives us ethanoic acid. So proper naming ensures clarity and standardization globally. So we must we must understand that structural and molecular formula. Molecular formula shows the number of atoms, e.g., C2H6O. That's the molecular formula for that particular, compound. So molecular formula basically shows us the number of the atoms, why the structural formula shows us how atoms are connected. How the atoms are connected, that is being displayed or shown by the structural formula. Ethanol, for an example, the molecular formula for ethanol is just C2H6O. That's the molecular formula, C2H6O. But structurally, it's a CH3, CH2 bonded to OH. So structurally, it is different. So the structural formula is CH3, CH2, OH, while the molecular formula is just C2H6O. So we can see how the atoms are connected in the structural formula. The molecular formula just shows the number of the atoms that are present. We have two carbons, you have one, and six hydrogen, you have one oxygen, and that's that for molecular formula. Okay, so drawing the correct structure is key in organic chemistry. So you can have this like acetic acid, acetic acid is another name for ethanoic acid. So when you have acetic acid, which is C2H3O2, this is how it is molecular formula, just C2H3O2. But structurally, it is like one carbon bonded to three hydrogen atom. The carbon is bonded to another carbon, and then that carbon is bonded with a double bond to an oxygen, then below bonded to the OH and all like that. So that is the structural formula. It shows us the connectivity or the way the atoms are structured or connected or formed, so to speak. Ethyl alcohol is another example, and this is C2H6O. Ethyl alcohol is just the same way as saying ethanol actually. So you see the way it is structurally, how it is written. So that's just the difference between structural and molecular formula. Okay, I hope we are getting the concept. Please let me pause and just say this quickly, that if there's an area that you don't understand or something I've said that you're not so clear about and you want me to shed more light, kindly go to the comment section and put your questions there. I'll look through them and then I'll give the right response to them when I see them. All right. So let's move along now and move to the next thing. And that's isomerism in organic chemistry. Isomerism in organic chemistry. So isomers are basically compounds with the same molecular formula but different structures. They have the same molecular formula but they have different structures. So that's what an isomer is. Structural isomers, this one, different connectivity of atoms. Example, butane, which is straight chain, versus methylpropane, which is branch. So we can have a structural isomer in which their atom, the connectivity or the way the atoms connect differs. If you look at butane, which is straight chain butane, is just a C, just four carbon bonded together, then hydrogen, about 10 hydrogens that are bonded to those four carbon atoms that are bonded hand to hand and like that. And it's still the same thing when you look at it with methylpropane, which is a branch, compound, so to speak. So that's what we call a structural isomer, because the only difference is just a change in their structure, the way they are arranged structurally. Then we have geometrical isomers, and this one involves the cis and trans isomerism, different spatial arrangement around the double bond. So when you have a different spatial arrangement around the double bond, you will talk about geometric isomer. So I can give an example with that one, like maybe you have a carbon-carbon double bond, then you have the hydrogen, maybe the two hydrogen that are just up there like that, bonding, side by side on the two carbon atom, and then you have the other two bonded like that, or revert if you want to talk about the other one whereby you have the C to C double bond, and then you have the hydrogen one bonded this way diagonally against the two carbon atoms. So that's why we have a trans configuration, a trans setup, so to speak. We'll talk more about this as we move along in this lesson. So isomerism explains the difference in physical and chemical properties of compounds. So let's look at these, like what I was just trying to explain, before this diagram is just this. You have a cis, isomerism and a trans isomerism. For the cis, you can see the methyl group. Both of them are on the same plane, connected to the carbon double bonds, and that's a cis isomerism for butene. For the other guy, we call the trans, you can see that they are diagonal to each other. One is on the one end of the first carbon, which is carbon 3. The other one is on the other end of carbon 2, and is diagonal like that. So that is a trans isomerism. So this is basically the difference between the cis and then the trans isomerism. Okay. So the next thing that we need to look at is the homologous series. Homologous series. And in looking at the homologous series, we say that the homologous series is a family of compounds with the same functional group. They have the same functional group, similar chemical properties. They have similar, chemical properties, and they have successive member differing by CH2. So the first member, the difference between the first member and the second member in an homologous series is just a difference of one carbon and two hydrogen. That's CH2. So that's the homologous series. So let's look at an example. For alkanes, we have methane, you have ethane, you have propane, and then you have butane. Now, if you look at it closely, looking at the table that is beside, sorry, let me move this a bit up here. Okay, looking at the table that is by the side, one thing you'll notice is that for methane, it is just CH4. Ethane is C2H6. What is the difference between methane and ethane? It's just a difference of CH2, CH2, basically, that's just the difference between them. Propane, butane, the same thing like that. So this is a homologous series. This is an example of homologous series for the alkane family. So that's just what the homologous series is. What you notice is that they have the same functional group, just a single bond, and then they will also have similar chemical properties too. And then the successive member had different from each other by CH2. Okay, so let's take note of that. Okay, so physical properties such as boiling point increases down the series. So the physical property, like take for instance, like the boiling point, it means that the boiling point of methane, hypothetically, if it is 70, what will happen to ethane? Ethane will be higher than 70. Propane will be higher than what we have in ethane. Then the boiling point of butane will be higher than what you have in propane. So that's basically what that connotes. Okay. All right, so the properties of hydrocarbons now, alkanes, they are relatively unreactive, and then they undergo combustion and then substitution reaction. So, and the reason why they are unreactive, just like I was saying the other time, is because they are saturated hydrocarbons, all the space or the places that they are supposed to form, bonds, has been taken up by an atom. So if you want to react, or if you want to get involved in any reaction, what you can see is just a substitution reaction, whereby you want to knock off one atom from the compound in order to bring in or introduce another atom, so to speak. So basically alkanes are relatively unreactive. They are reactive to an extent. So we said relatively they are unreactive. They undergo combustion. Yes, when they undergo combustion, they will form carbon dioxide and water, and then they undergo substitution reaction. Then alkenes and alkynes, they are more reactive due to the double and triple bond. And then these ones differ from alkanes in the sense that they undergo addition reaction. Don't forget that they are unsaturated. They are willing to take on more atoms, and the coming in of more atoms will break their double bonds or their triple bond, as the case may be, So That's that for that. So combustions of hydrocarbons now. When you have methane involved in a combustion reaction that is reacting with oxygen, like I said earlier, it will form a CO2 and then H2. H2O. Please pardon me. Okay, so fuels burn to release energy needed in homes, industry, and transport. So this is the basis for the fuel industry, whereby the fuel in your engine or in your vehicle, you put in petrol and then it mixes with oxygen, it burns, and they generate the necessary energy that will propel your car and keeps moving your car and the likes like that. So the same thing with our gas, the LPG gas, the LPGs that we use at home, that's the liquefied petroleum gas that we use at home. It's combusts, as in it mixes with oxygen, and then it creates the light, and then that supplies the heat to cook our food and to do so many household activities. Okay. So reactions of functional groups now is the next thing. Alcohol can combust. That combust means that they can react with oxygen. They can react with acids to form esters, okay, which we call esterification reaction. Carboxylic acid will react with base to form salts. Take, for instance, you can have ethanoic acid reacting with sodium hydroxide to give us um, um, sodium ethanoids, which is a kind of salt. Then we have esters that are formed by the reaction between an acid, like a carboxylic acid, and then an alcohol. Okay. So some of these examples, you have a carboxylic acid reacting together with ethanol or methanol in this case, to form that salt that we have there, and that is methyl methanoid. Sorry, methyl ethanoid. Yes, methyl ethanoid and plus water. Okay. So we have the acetic acid plus methanol to give us methyl acetate plus water. So esters basically have fruity smells and are used in perfume, and that is what is formed there. The methyl acetate is actually an ester, so they have fruity smell and they are used in perfumes. Okay. All right. So addition reactions of alkanes now. Alkanes react with hydrogen in a process called hydrogenation. A very good industrial application is in vegetable oil to margarine rather, whereby you go through hydrogenation of vegetable oil to give us margarine. So it moves from just a liquid to become a solid, which is like margarine. Sorry, margarine. Pardon me. So that's an hydrogenation, and it occurs with alkanes. So it's an addition reaction. They also go through an addition reaction whereby they are added to halogens, and this is a test for unsaturation. Like bromine water would decolorize when it's combines and so on and so forth like that. So it can also add up with halogens, chlorine, fluorine, bromine, and so on and so forth. So you can have something like this when your ethane react with bromine to give us bromoethane. So that's that for that. So addition reaction are useful for making plastics and pharmaceuticals. They are very, very useful for making plastics. So you can make plastics, you can make PVCs and the polyvinyl chloride and so on and so forth like that, from addition reactions involving alkenes. And then you can also produce different pharmaceuticals from addition reaction involving alkenes. Okay. So polymerization is another thing that we need to look at. And polymerization is the process whereby small molecules that we refer to as monomers join together to form large molecules that are referred to as polymers. So the small molecules, monomers join to form large molecules, and we call them polymers. Okay. So there are different types of what's it called, polymerization. We have what we call the addition polymerization. Here monomers had without loss of water or loss of atoms. Example, ethane polymerizes to form polyethylene. So this is an addition polymerization whereby the monomers just add themselves up, and then there's no loss of any atom whatsoever. That's addition polymerization. It's a form or it's a category of polymerization. So we can have something like this, small molecules of ethene coming together to form polyethene, okay? We can also have what we call condensation polymerization, in which the monomers join with the loss of a small molecule like water, even methanol sometimes. So example is the formation of nylon. So it's an example of a condensation polymerization. So polymers are essential in making plastics, textile, and synthetic material, and so many other materials too. Is as a result of polymerization. So polymers are very, very essential in making some of these items that we see in our house that we make use of on a daily basis. So basically what we have the monomers coming together to give us the polymer, which is polymerization. All right. So what are the uses of organic compound? What are some of the uses of organic compound? One, they are used as fuels. So we can use them as for petrol in our vehicle, diesels in heavy trucks and engines, and then LPGs for cooking, liquefied petroleum gas, for cooking and so on and so many other functions too. Then we can have them used as plastics. They are used in making plastics like the polythene bags that we use in packaging items when we go to purchase things. These are made from polymerization, and these are some of the uses of organic compound. They can also be used for making different containers, water bottle, plastic bottles. It just to mention but a few, so many items. So it is the organic compounds that can yield them. So they're also very useful in medicine. We in the world of in the pharmaceutical world, you discover that there's a way that they manipulate carbon atoms in such a way that it will produce certain, useful medicine that has been of great and tremendous help to humanity. Like let's take for instance, like the antibiotics now, the analgesics that we use for pain to relieve pain and so on and so forth. These are medicine that have been formed from organic compounds. We also use organic compounds to produce urea, which is organic nitrogen fertilizers, very, very important in the agricultural world and for food security and for food to be abundant. So fertilizers are also made from organic compounds. So organic chemistry touches every aspect of modern life. The clothes that you're putting on, the cup you're using to eat, to drink, rather, the plates that you're using, the spoon, and so many other items that you make use of are all products of organic compounds. So it touches every aspect of modern life. And that's why most of the time we say what in this world is not chemistry. Because chemistry, organic chemistry to be precise, is very, very germane to so many things that we have available that are very useful to us as human beings. Okay. All right. So let me summarize this lesson. And please, if you have any question, please put them in the comment section for us to, take a look at. So organic compound revolves around carbon bonding. We have talked about it. It's the chemistry of carbon that gives us the ability. And it's just because carbon can go through what we call catenation, whereby it can bond to each other end to end to form long chains. So organic compound revolves around carbon bonding. Proper naming and understanding of functional groups are essential. Proper naming and understanding of functional groups are very, very essential. We talked about it and the rules that is involved for naming compounds. So hydrocarbons are classified based on the types of bond that they have. So you can have alkanes, which is the single bond, alkanes, double bond, then alkyne, which is the triple bond hydrocarbon. Then reactions like combustion, substitution, and addition define chemical behaviors. And these are all, peculiar to different classes of hydrocarbon. They all undergo combustion to give us CO2 and H2O, just like we talked about. We said that alkanes are the only one that goes through substitution. Then addition is peculiar to the unsaturated hydrocarbons, which are the alkanes and the alkynes, okay? We also talk about polymerization, whereby we use it to create larger molecule, whereby monomers, which are the smaller molecules, join together or bond together to form the larger molecule. And the knowledge of polymerization has helped a lot. It is used in producing materials that are very, very important for our day-to-day activities. Okay. All right. So I think there's a mix up somewhere. Okay. Let me quickly pause here. I want you to also put your response in the comment section. So if you have any, just please do that. Put it in the comment section, and then I'll take it up from there. So we have looked at we have looked at all that in the course of our lesson. And like I said, if you have any question or you have an area that you want me to expatiate on, please don't hesitate to bring it to my notice by putting it in the comment section. So we want to look at some few questions to evaluate this class. What is the general formula for alkanes? Alkanes basically have the general formula CnH2n plus 2, CnH2n, CnH2n minus 2, CnH2O. So please tell me which one do you think is the answer in the comment section. Okay. But if you look at them critically, the answer to that one is CnH2n plus 2. Which compound is an alcohol? Is it CH4, CH3, CH2OH, CH3, COOH, or CH2 double bond CH2? So let me know what you feel the answer is in the comment section. And then if you look at it critically, you discover that the answer to that one should be B, CH3, CH2OH. What type of reaction occurs in ethane plus bromine? What type of reaction occurs in ethane? Ethane plus bromine. When you have ethane and bromine coming together, is it a combustion reaction, an addition reaction, a substitution reaction, or an elimination reaction? We've talked about this before and in the course of the lesson. So let me know what you feel the right answer is in the comment section. And if the answer you chose is A, that means you're wrong. If the answer you chose is C, you are also very wrong. But if you have chosen option B, which is addition reaction, that is very, very correct. Okay. What is formed when ethanoic acid reacts with ethanol? So when you have an acid reacting with an alcohol, we said it will form something. And what is that thing that is formed? Most times it is actually forming an ester. So let's look at it together. Ethanoic acid reacting with ethanol. Will it give us methanol? Will it give us ethene? Will it give us ethyl ethanoate or water only? So let's look at the options. And if you look at it critically, you will agree with me that the correct answer to that one is ethyl ethanoate, which is an ester with a peculiar fruity smell. And we said it is deployed in the perfumery industry. All right, thank you for joining me in this lesson. That brings us to the end of this particular lesson. Please, if you have any question whatsoever, don't hesitate to put them in the comment section. All right, bye-bye for now. I'll see you in the next video.